So I have 20% volume percent of hollow micro balloons having wall thickness as 5 microns. For 20%, I'll get one property for wall thickness of 5. Now keeping the same volume fraction as 20, nothing but 40 micro balloons in a given resin. If we increase the wall thickness from 5 to 10 microns, I have got one more set of property. So what does this mean is, as compared to our general composites phenomena, wherein we have X versus Y, wherein X is volume percent from, let us say, from 0, 20, 40, 60 to, and on the y-axis we have a property moduli, compressive moduli, or whatever you have property you want to investigate. So here, for the same 20 volume fraction, for one wall thickness, I am going to have one curve. For again another volume fraction, another wall thickness, I will have a different property trend. And if I go to 40, 60, so in a short, in foams, closed cell foams, nothing but syntactic foams, I will have one more Z direction in addition to X and Y, wherein the Z is telling me the wall thickness variation. And this is what the beauty of these hollow micro balloons renders as a range of properties. So we have wide range of properties. And when I say we have wide range of properties, I believe that you got my point, that what I mean by wide range of property. One thing is wall thickness variation. Another thing is volume fraction variation. So this gives me an additional axis wherein it gives me an additional property range and property plot. And when we say we have a material system which gives us wide range of properties, that means I can cater the application to aerospace, probably automobile, marine, and so on and so forth, even for a biomedical application. And that's how I landed up with this material system long back and still exploring that. So in addition to this wall thickness, volume fraction, we have size distribution, and so on and so forth. Typically, this is particulate system. And this gives me also one more flexibility, that I can model this mathematically very easily, because these are properties, these are particles which gives isotropic properties. Similarly, I can simulate them as well. So in addition to experimental, we can go for a mathematical modeling and support, and thereby, in addition to that, even a simulation packages. So where does the syntactic foams are used, and what are those different, whether shapes are available? Yes, there are cuboid shapes, cube shapes, even spherical ones, but we prefer spherical ones because we will not have the stress concentrations across these corners as we are going to have for cuboids or cubes. And thereby, we prefer spherical ones. And in spherical ones, again, there are two resources. One, engineered one, meaning these are manufactured, like glass microballoon. Second, naturally available ones, like fly ash cyanospheres. And we all know that fly ash cyanospheres are the waste byproduct of a thermal power plants, which are dumped and which are environmentally hazardous. So if you choose a fly ash, then you are satisfying multiple strings. You can reach out to the society well, you can synthesize the material, as against in the glass, which are engineered ones. So our group has explored both these. What are the applications of these foams? In aviation, as thermoforming plugs, you can see a thermoforming plug here. Especially, these are used in thermoforming plugs because these have minimum coefficient of thermal expansion because of the hollowness. Then these are also used in seashore applications, wherein crude oil is taken up somewhere deep in the sea to the shore, wherein pipe has to be laid. And if you just lay the pipe in the water, because the density of this entire pipe with the fluid is more, it sinks, ruptures, and there is oil leakage. And thereby, these pipes are roped into these yellow modules, which you can see it down the line here. These are known as a flotation modules. When you put this in, their density, total density goes much below 1, and thereby pipe is floated on the water, and we are reducing that rupture phenomena. And this material is not new. It is very much old system. Only how these are being manufactured, how these are being synthesized, based on advanced technology, the routes are changing. So this is human-operated vehicle Alvin, which is used to find a wreckage of a Titanic. This is completely a syntactic foam module. Then we have remote operated vehicle. This is human operated vehicle, remote operated vehicle JSON, wherein these are used to maintain the underwater pipelines. Then we have ships. Zumwalt is another military establishment module wherein they are using syntactic forms. Deep Sea Challenger down here is being used by James Cameron. Then we have memship nuclear submarines. Everywhere these syntactic forms are used. Okay, so my group has exploited high density polyethylene with Sinospheres. This is, as I mentioned earlier, environmentally pollutant one, and then engineered one, that is a glass microballoon. Now, whenever we decide one material system, so we need to do a lot of groundwork about how much percentage we can go for. And if you keep that same from first material until whatever material you are exploring existing, then it becomes easier for comparison, like we can compare apple to apple. So thereby, we kept 20, 40, 60 as constant. And this to reach to 20, 40, 60, we did a lot of trial and error in the sense what happens below 20, what happens above 60. And that's what experience I have mentioned here. So if you go below 20, this lower particle loading provides higher density. And that is not admissible for marine system, even any lightweight system, which lightweight components which can be used in any weight sensitive structures. And above 60, particle, there will be huge number of particles which interact each other. They will impact on each other and then they break when we go for processing, let it be compression molding, injection molding, or extrusion or 3D printing. And that's why this 20 to 60 is kept constant for all my works based on these fundamental work which we have done through simulation, mathematical modeling, and also through experiment. So we have utilized these. Matrix is kept same, high density polyethylene. And then because this is again, high density polyethylene is widely used in consumer market. So if I use fly ash Sinosphere and reduce the plastic consumption here, I am hitting the right button. The same way with the glass microballoons. And that's why we went with high density polyethylene in a virgin mode as well as in the recycled mode. So typically, as far as this talk is concerned, I'll just have these two methods. I'll start with this and end up with this. So we have exploited injection molding earlier and then shifted to 3D printing. And in 3D printing, typically this fused filament fabrication or fused deposition modeling. Now, what happened in injection molding as part of my first PhD student in 2016 who defended at that time, we could able to synthesize HDP with Sinosphere, and we shown that we can reduce the consumption of HDP and we can infuse that with the fly ash Sinospheres, which is an environmental pollutant. And as an outcome of the thesis, these are the components which we injection molded, which are regularly used. So what is your centrally you are seeing are the virgin plastic, and then what you are seeing in the outer periphery are all with fly ash Sinosphere with a specific percentage. So that was his part of a PhD. But across all these gray colored components, now why this gray color comes? Because fly ash is of a gray color. So what happens is across all these components, there is component number 3, which is a gear. I'll just focus more on that. If you see this gear, you can see this circled zone. Now, if you see this in circle zone, there are some white patches present here. So what does this white patches means is fly ash Sinospheres could not reach these zones. The reason is thick to thin section and complex geometry. So this is what we found out as the outcome or the problem of the first PhD graduated. No doubt, other components came well, absolutely not an issue here, but this is where we say that, okay, injection molding is not working for such a complex components, which is fly ash and high density polyethylene, but we need to find a solution for that. And that is the first DHT project which I got in 2016, proposing the solution for this through 3D printing technology. So in 2016, we started with this 3D printing work, and whatever presently we are doing, that I'll be presenting as part of this subsequent slides. So in 3D printing, as we all of us know, that we start with a 3D CAD file, and then we create a model. We can scan it even if you want to go for a reverse engineering. And this CAD file in STL format is fed to a machine, which reads G codes. So STL file gets converted equivalent to G code, and then G code is been fed. And what this FDM based on triple F fused filament fabrication machine does is it goes on laying it layer over the layer. So this is how it happens, and finally we finish the product through appropriate solution or sandpaper to make it smooth. But still, we have always the issue of these gaps, or we call it as the bulges, because of layer formation. So this is what technology I'm going to talk about. So we have a filament. So this filament is nothing but, in common layman's language, a plastic wire. This plastic wire, you can bring it from, or you can procure it from the market. There are very large establishments, many establishments, commercial establishments, which will give you filament in a ready form. Then you fade it, and there is a head here. This head pulls it, melts it, and then deposits on a platform. And this is what typically fused filament fabrication goes for. But when you deposit on a platform, this compatible material you need to have as a substrate material, and over to which you will print the first part and then go on building complete model. So what we do is, what sketch you are seeing it here, a 3D printer is here. So this is FDM based 3D printer, which has a built volume, a printing volume of 0.5 cubic meters. I can go up to 450 degrees C temperature, and I can operate this printer now through IoT and so on and so forth. This is we procured in 2016 under the first DST grant. The cost of this is 20 lakhs, 20. So here I can try all sort of materials, and that's how the features get added up and the cost goes up. And on this machine, we never used any commercially available filament. So we rather manufacture the filament through a blender here, which you can see it here, polymer blender. So we add a polymer and the reinforcing agent or filler, blend it. The blend comes in the form of solidified pallets. These pallets, we load it into, this is a single screw extruder, what I have in my lab. This is again, entire setup is through DST grant of 2016. So we feed pallets here in the hopper of the extruder. No doubt polymer blender parameters you need to optimize. And when I say optimize, meaning you need to optimize in terms of good dispersion. And if you're using anything hollow, they should not break. So there are a lot of trial and error methods happens here. And then the same pallet, solidified one, goes into the hopper of an extruder. Then again, we have different parameters here, screw speed, takeoff speed. Then there are 4 heaters. Then optimization of these to get the filament. And that filament is nothing but what you see it here. So we manufacture our own filament in the lab. So this filament, we feed it to a 3D printer. And then again, there are a lot of optimization parameters will come that you need to really look into. So typically, when we talk about filament development, we have a barrel temperature, die temperature, screw speed, and takeoff speed. The temperatures here, you can take a reference of TG, melting point, and the degradation point. So these 3 values will decide what should be the barrel temperature, die temperature for a specific blend, which you have loaded into the extruder. Screw speed and the takeoff speed again. The screw speed is dependent on, if you're using a hollow system, the crushing strength of a particular particle. or if you are using any short fibers, because there is no filament available presently, as far as my knowledge goes, which has a continuous fiber. Although people claim, though many companies claim that they can print continuous fiber, those are not continuous fibers. Continuous meaning full length. So these are all short fibers. So again, the screw speed is dependent on the short fibers tearing strength and shearing strength. So all those parameters, once you take into account, then you will be set up a screw speed. Half of that would be generally a takeoff speed. The ratio between screw speed and the takeoff speed will determine the filament diameter, because this is most crucial element. The filament diameter has to be controlled within range so that the printer will print it correctly. Else, either you face a clogging or you will face a more material. If the filament diameter is less than what is prescribed or what the 3D printer wants, then you have sometimes breaking of filaments as well. And if the diameter is more material comes, and all those many parameters will affect them. So this is how in extrusion, you need to take an extreme care about maintaining the filament diameter consistently, and it is possible if we go with scientific support and temperature and the speed, the shearing strength, the tearing strength, everything is possible, not a big deal. Then we have a 3D printer. In printer, we have a printing temperature. Again, it is dependent on what, as I said, TG, melting and degradation temperature. Then we have a chamber temperature. Chamber is this completely enclosed chamber. Now, we use this chamber temperature when we try different materials, semi-crystalline polymers. Then we have a base plate temperature. This is the base plate, which I was talking about in the previous slide. Sorry, yes, here. So this is the base plate, a gray color one platform. On this, we are going to print the first one. First layer is getting printed. For many known polymers which are there in the market right now, we don't require at such platform temperature, but for many composites or many semi-crystalline, crystalline systems, we need to have some temperature here so that the gradient between the first printed layer and the your platform temperature is should be very low. Else, there will be thermal stresses, and then the warpage comes in picture, and thereby we need to choose that appropriately. So that is what the base plate temperature parameter comes in, and then the printing speed. Again, here printing speeds nothing but flow rate. It depends on what composite system you are using, and it directly depends on the melt flow index of the composite filament which you have developed. So we can have a mathematical backing for that, and through that you can come across a proper printing speed. No doubt, in experimentation, you need to spend a month or so to just optimize the things, because optimization is one, consistency is the second. How consistently with the same parameters your components are coming, that is most crucial. And that's how you have to be extremely careful. Right. So as far as our lab is concerned, I'm just showing only a few limited cases here. So we have extruded successfully high density polyethylene filament. As I said earlier, we don't buy anything, or even high density polyethylene filaments we manufacture on our own. So this with fly ash, which I shown it to you in the earlier slide, is this filament which is seen in the gray color. We have extruded the elastomers as well, and elastomeric composites, and then we have printed these composites as well. So this machine is a very rugged machine, and which gives me complete flexibility to try everything for that matter. Even we have mixed stainless steel powder, brass, copper in the polymers, and we have printed it. And still it is giving me a work. So the warranty of 3 years is over in 2019. So whenever you go for a machine, please be sure with how rugged the system is, what all flexibility it gives it to you, and what all materials you can explore. Then some machines which will have a limited capability of handling the systems. So now what happens when we try with something different material system like high density polyethylene and this fly ash cyanosphere. Now, as all of us know, fly ash cyanospheres are naturally available. They have numerous defects, and that gets carried over in your synthesis as well. So this is these are the two micrographs which I am showing are the first trials of this filament extrusion. Rather, these are the micrographs of the samples which are not which should not be synthesized. Rather, these are the failed samples, and still I am presenting it because this is the experience which we have gained. So in this micrograph, which you can see it here on the left, is same fly ash, high density polyethylene and fly ash, but as though we optimize the parameters, still you need to do the fine tuning because in experimentally than the theoretically or mathematically regime is altogether different. Right. So thereby, this is the filament wherein you can see a core shell type structure. Some particles are seen here, some were here, graded system, but it is highly non-uniform. And if I take a micro CT of this, this is how the filament looks like. So I hope you got the point that I can't fit this filament in the 3D printer because this is more or less an oval one. So we need to again tune the parameters. Specifically, in case of this ovality, if you want to make it circular, then you need to tune in screw speed and the takeoff speed. And just a little bit, 1 or 2 days, you will be able to get a completely circular one. So this micro CT gives us more or less, even though SEM will also give me this shape, but I can see even the distribution well in micro CT than the scanning electron microscopy. So this is the next slide, wherein we got all the parameters optimized. And this is the circular one, which you can see it. A is our 60% by weight cyanospheres in HTP. What do you mean by 60% by weight? By volume, probably it is around 73 or 74%. Okay. So by that amount, we could be able to successfully load a particular resin. And what does that mean? If I say 75 by volume is my cyanospheres, then only 25% is the matrix. So I can save 75% of the matrix if I develop this filament in, if I can print it. So what you see here is all these small micro balloons. In addition, you can see some pockets here. So what are these pockets for? These are definitely not the balloons. And these pockets are the air entrapment. And these actually them, you quantify them, and give the subsequent justification. Reviewers agree because they know it. And now, what is the reason for such air entrapment here? The reason is the machine which I have used. And what is that machine? I said it's a single screw extruder, right? This single screw extruder is non-vented type, VENTED. What do you mean by vented or non-vented type? Vented types are those types wherein we have a specific vent to take out the flue gases, which gets generated, developed in this barrel of your extruder. And if you have a vented type, you can take out all those gases, flue gases, and what you will see here is the filament cross section without any pockets. One thing, fine, but I don't have that vented type. So I said, yes, this is what I can produce with my existing system. Additionally, what happens is, because there are entrapped air pockets here, let us say by infusing 60% cyanospheres in this filament, I'm reducing the weight by, let us say, 30%. That is the maximum, right? So above 60%, if you go, particles will fail, and if the particle fails, density will sharply shoot up. Rather, instead of filament floating, it will start sinking if the particles break. So now what happens if I have additional air pockets? So I can go even above 30%. So with 60% micro balloons, I can maximum reach to 30% weight saving. But if I have such entrapped airs, my density will still go down, and probably I may achieve much more than what individually these microballoons can do. And specifically in compression, damping, cushioning, energy absorption, and impact, these voids will play a major role, and they will absorb some of the energy, and energy enhancement can be seen. And you can justify that way also. So if there are any voids, if there are any cracks, don't say that we got a perfect sample, which is not possible, because our manufacturing methods are having variations, and those variations will reflect them. And then what we did here is, this is one-time extruded, right? Then we checked the recyclability potential of these filaments as well. So what we did, we took that one-time extruded filament, we chopped it again. So chopped it meaning we converted that into small pellets, loaded again in the extruder, and extruded one more time. And that becomes two-time extruded, 2x. Then we conducted some test, and then again we took the second time extruded filament, chopped it again, and loaded in the hopper of the extruder, and again we drew the filament. We call it as a three-time extruded. Now here, all these micrographs are having, especially the D, micrograph D, is three-time extruded filament, which is showing that these are the microballoons, which you can see this spheres, and these are pliers, right? So thereby you can see some defects here on the particle as well. So even though you have extruded 3 times, these particles are intact. And that's how the optimization helps you, or trial and error method helps you out in coming down to that. So now again, we tested 3-time extruded filament as well. So by extruding 1 time, 2 times, 3 times, we shown that there is a recyclability potential in the extruded filaments. And one more, I wanted to share just a view that generally you have seen these micrographs, right? Now, what is this micrograph? Micrograph is an image at a particular location. And many of the times, what generally people do is they take a micrograph wherein the distribution is uniform. There are no failures, no cracks. But as a reviewer, if I want to know that this is whether it's taken at one location only, I can ask you a question in the revision that I want a micro CT across 3 different planes. And there is where many people fail, and we reject the manuscript. So one more way is you take a micro CT at 3 different planes. Plane 1, the image is here. Plane 2, the image is here, and plane 3. Across 3 different planes, and then we ask them to present. Now I want to just share one experience here of micro CT as well. Micro CT, you can just take it to find out the distribution. But if you want to comment based on the micro CT, there is one small suggestion for which goes in. Now, I'm just looking at the micro CT, figure D1. This is the slice 1. So there are multiple slices. You can take the micro CT of the entire region. So slice 1 is at the front. Slice 2 is just back of the slice 1. Slice 3 is at the back of the slice 2. And slice 4 is at the back of the slice 3. And what is the difference? The distance between slice 1 and 2? Probably 0.05 microns or so and so forth. So it is not at a different far off places. It is just the next slice. Now what happens here? If you look at this red marked circle, okay, and that red marked circle is, I'm looking at slice 1, is pertaining to 1 microsphere here. Now, when you go to the slice 2, you can just see at this moment there is some loss of white color. In slice 3, for the same microballoon, now what it shows is there is a crack or a gap. Then again, in slice 4, the gap is been closed. So what I mean here is, if based on slice 3, if you comment that the microballoon is broken, that is wrong. The same microballoon, when we take at different slices, is sometimes showing there is a gap, nothing but a crack or broken one. At some places it is showing a perfect one. Why does it happen? So what I mean by this is, don't go by only one slice and interpret or apprehend on that. So take multiple slices and look at that. And why this happened? There was no crack, little crack, a large crack, and again the crack closes. Because this hollow microballoons of fly ash ionosphere, which are naturally available, no, these are having porosity within and even porosity in the shell. You can see it here, all the marked ones, and this is naturally available. So your shell is also porous, and that's why this is used in the cement industry from a decade now, which absorbs the moisture, and that's why we call it as a pozzolanic cement. It absorbs and it grows and closes all the cracks in the cement structure, and that's how it happens. So when you take a micro CT, please take a note of this and have specific apprehension on that. So as I was mentioning about the filaments which we developed, so here is the filament which is 3-time extruded, tested at 3 different strain rates. It is simple tensile test. Now, why 3 different strain rates? ASTM says 10⁻⁴ for an example. But why I should spend time in going for 10⁻², -3 and -4? Because 10⁻², means one application. -3, a different second application. -4, the third application. 10⁻², another application. 10⁻⁵, probably we are looking at the material, developing a material for blast proof protective gear, right? So this is how it does. So same test at a different rates, we need to go into to find out how the property changes, or whether for a specific application it is giving you a specific response or not. So here 10⁻², -3, -4, I can just give an example of your footwear. Your footwear has a sole. When you are standing, it's the, in all the cases, for a footwear, it is the compressive load. When you're standing, compressive load, for an example, 10⁻⁴. So when you start 10⁻², when you start running 10⁻⁵, when you start jogging, probably 10⁻².5, and so on and so forth. So if you want to know your material, or if you want to develop a material and look for a specific application, or you have a specific application and you want to develop a material, find out that strain rate, what is that loading? And for that loading, you need to have the testing done. So ASTM standard says 1, that is to have the, what you can say, the same material. If I can test it in US at New York, I should have the similar features. And that's why that is a standardization. But it never says you to stop at that only. So based on blast, based on underwater applications, this strain value changes. And that's what I wanted to make a point. So here, the figure F, what it shows is the specific modulus versus strain rate plot. And here, I want to make one point very clear that now, okay, fine, you have developed a filament, but before going for 3D printing, you should assess it, whether I may get some better properties in 3D printing or not. If you're not getting it, then there is no point. It doesn't make any sense for exploring 3D printing at all. So how we did it, as I said, we started with injection molding. So same composition, we took it. And then this is HDP40, also investigated with injection molded samples. Please do remember, HDP42X, HDP43X are the filaments. And whatever you are, I'm marking here, injection molded, these are the tensile samples of type 1. I repeat, injection molding is the type 1 tensile sample performance, and these two, HDP42X, 3X, are filaments. So I am comparing the filament with filaments tensile behavior for the same strain rate as that I've done for tensile tested sample. And what I did see here is the 3 times extruded filament is performing better than the tensile modulus of the sample, complete sample type 1. That means definitely I should go for 3D printing, because my filament itself is performing better than the injection molded sample. So what it gives us a confidence to us is, if filament is performing so well, then if I 3D print it of the same type 1 and compare it with the tensile modulus of injection molded one, it is definitely going to make a sense, and it will be a good case wherein 3D printed samples will perform better. So this one counter check, we did it. and I think this would be a feasible option when you go for a materials development. So don't go by just looking at some fancy names of this filler with that matrix, and then you invest some money in testing and all those things, and finally you come up that the 3D printing is not doing well, or even filament is not getting extruded. So this is just my experience I'm sharing. I'm not a boss of anything for that matter. So I'm just giving some inputs. I may be wrong at many places, but these are all my experiences. So as I said, when we say printing new materials, other than ABS, nylon, whichever are available in the market, this is what we face. Okay, so as I said, HDP printing. When we started printing HDP, you can see in the first figure here on the right, left-hand side, the material got deposited well at some places. It doesn't deposit anything on the other. And most importantly, what happens is after printing is done, you can see this warpage in the right-hand side first row image. So this is what is the sample. I guess my cursor movement is also seen. Hello, whether the cursor movement is seen on the screen? Yeah, I guess yes. Fine. I'll just go ahead. So here we have a sample, and then the sample is printed on the base plate. Even it has made the base plate to get warped. And this is what is a serious issue when you try different crystalline, semi-crystalline materials. Then you have to optimize the printing parameters as I mentioned earlier. And then what you see at the bottommost image is the perfectly printed type 1 tensile printed sample, which we compared with compression molding, which we compared with injection molding. So here one point to note is, we should never say that HDP is ductile. It depends on the processing route. Injection molding, definitely it is ductile. You can see a long necking and broom-like failure. Compression molding, it's direct crack. 3D printing, the fibrous failure again. So you need to always look into what is that processing route adopted to realize that. So this is the same pure HDP, which we looked at the 3 different routes and the failure mechanisms. So this is how HDP looks like in B, figure 1B. The figure 1A is whatever has been procured from the market. If you see a CM, it shows good feature without any defects. And I said glass, which is engineered, which is manufactured. And you can see the micrograph at 250 magnification. All are of almost similar diameter. Even though even if you want to just make sure that you use a particular diameter, then you need to go for a sieve analysis, particle size analysis, and then use them. So these are perfectly spherical without any surface defects. And definitely that should give me a good properties than the fly ash as well. What you see in figure 2 is one such developed filament, more circular in nature. And this edge, what you see in figure 2A, is because of we use the knife. Because these are all ductile systems in the filament form. So even though you put it in the nitrogen for a day or a week, and then try to break it, they will never break it in a natural freeze fractured mode. So we need to cut it through a knife. And you can see this knife marks, the polymer flow lines. These are just following the knife lines, and you can see all these micro balloons intact there. And this is what we actually produced a system with different filaments and different material systems and compositions. And type 1. Yeah, so table 1 shows you all the different parameters. So here we developed the blends of HDP and JMB using Brabant, or the polymer blender, which I shown it to you, to develop the feedstock foam filaments, because we are using the syntactic foams here. And what I'm going to talk next is, I already shown to you that we can print the samples, right? So syntactic foam samples is not a big issue. Now I'm going to talk about printing of a sandwich. So that's what the same work we carried forward next. Once you resolve the issue with the pure HDP and HDP with 20, 40, 60 glass microballoons or Sinospheres, fine, you can print the samples and do the routine work of testing them, having a different properties and so on and so forth. So what is the next level? Can I print a sandwich out of this? And that is what I'm going to just talk about a second opportunity after talking about the foam opportunity and the issue there. So blending is carried out at an optimized speed. Again, when I say optimized, a lot of trial and error method has gone. So we have carried out at around, I think 160 degrees C and at the blending or polymer blender speed of 10 RPM. And we infused 20, 40 and 60 by volume of GMB in HDP. Now these three different volume fractions, we denote them henceforth. If you see some numbers as H20, H40, H60, H is for HDP and 20 is that volume fraction of the filler which we have used. So these HDP, sorry, yeah. So these blends of H20, 40, 60, we blended them. We initially dried them so that we can remove the moisture. Drying we carried out at 80 degrees C in an oven for 24 hours and then fed to extruder, what I shown it to you. Then for our work, we kept the temperature profile in this extruder from 145, 150, 155 to 145 degrees C from the feed section wherein the hopper is connected to the die section wherein the filament comes out. And again, as I said, the screw speed and the takeoff speed are crucial to maintain the filament diameter. So for our filament, we extrude the filament of diameter 2.85 millimeters plus minus 0.05 millimeters, because this is what the 3D printer prescribes us to maintain the filament diameter. And for maintaining that, we kept the screw speed of 25 and the takeoff speed of 11.5. So these numbers change for different materials. And so there is what one more crucial fine tuning comes in once you optimize the parameters. And then we studied the rheology. Then we checked how many particles have failed, what is the porosity. And then all these parameters we controlled. And then what you see, as I was talking about, figure 2A, it represents a circular cross section of an extruded H60 filament. So maximum loading of microballoons in the HDP. Other H20 at higher magnification, you can see it in figure 2B as well, wherein I was talking about this flow lines. Again, here there are no particles failed. So higher the particle survival, lower would be the density. If the particles fail, now the density, let us say, is 0.6. of the composite system, because marine systems require some specific applications wherein they want to go 4,000 meters deep down the sea. We have a buoyancy effect coming in picture, and for that buoyancy, we need to achieve certain density level. So let us say they want 0.6. Now, if your manufacturing method is not consistent or it makes the particles to break here, what happens? Now, I'll tell you the density phenomena here. The density of this hollow microballoons is 0.4, okay, intact, meaning non-broken ones. Now, if this particle breaks, this particle is made up of glass. So if the particle is intact, the density is 0.4. If the particle breaks, so what would be the density? The density is going to be the density of glass, not the balloon. So what is the density of glass? 2540. So 0.4 to 2540, it suddenly shorts up. So that's what I was talking about. The filament might sink or float based on the number of particles which are survived there. So to B also in micrograph, you can check them. So these are the intact microballoons and uniformly dispersed. And then once we formalize this, and then the production routine starts. You set the parameter, you extrude the filaments. And that's what I extruded filament of HDP with 60% of microballoons embedded in them with no fracture or breakage of the microballoons, no doubt there are entrapment of voids because we are using a non-mented type extrusion. So that's how it goes. Sorry. Yeah. Then we thought of printing sandwich all at once. Because all of us know that when I say sandwich, the core, the central part, is manufactured differently, and you have the slabs available. Then conventionally what you do, you take the jute skin or whichever skin you want, glass skin, dip it in the epoxy, put it in the mold. So you prepare a bottom skin, then place the core on top of that, and then on top of the core, you again prepare the top skin with dipping it into the epoxy resin or compatible resins for that matter, which you want to use, and then put it on the top, close the mold from the top, allow it to, if you are using Lapox L12 epoxy resin, I think we generally go for 24 hours of clamping it and giving a time to settle. After 24 hours, you remove it. Then what you have here is a sandwich. But what is the serious problem in this conventional manufacturing of sandwich? The serious problem is the interface between the skin and the core. You use whatever best adhesive you have. Still, adhesive is present at the interface. Now, what is an adhesive? Adhesive is not the parent material. So wherever there is absence of parent material, the strength of the system is definitely going to be the minimum, or the sandwich is going to be the weakest one. Just a minute. Yeah, I'm sorry. So whenever you use a conventional manufacturing method, the sandwich is going to be the weakest at the interface. We have a delamination, shear, everything happening. Let us say you have eliminated that by using an excellent adhesive, but still there is an adhesive. And this adhesive is not the parent material. What do you mean by parent material? Neither the skin nor the core material. And that's why wherever there are joints, these joints, let it be even any conventional joints. Joints meaning there is absence of parent material and material fails or buckles or have failure mechanisms governing from that point. Reason is parent material absence. So this is what we want to resolve, and thereby we exploited 3D printing in printing the sandwich all at once. Okay. And that's what we did it. Now, as you all know, it is very simple. It is nothing great, some groundbreaking research we did. I'll tell you what we did. I'll go back to that printer. Yes. Now, you know that all these FDM-based 3D printers typically comes with two nozzles. Only one nozzle is shown here, but these all printers are with two nozzles. One nozzle is for your actual material printing. The second nozzle is for support material. So what we did, we removed the support material filament and we put the composite filament in the nozzle too. So if I want to go by this sketch of sandwich, yes. So the bottom skin is printed with nozzle 1. Once, let us say this is 1 millimeter. 1 millimeter layer is built. Nozzle 1 goes off meaning it is there. But nozzle 2 starts printing the composite for, let us say, for a height of 6 millimeters. Then, after nozzle 2's printing, nozzle 1 again comes back and starts printing the top skin. So in nozzle 1, I have an HDPE filament. In nozzle 2, let us say I have a HDPE with 60% microballoon or a composite system. So here, by exploiting both the nozzles in 3D printer, you can print the sandwiches all at once in C2. Okay, or we say concurrent printing. So there is no adhesive. The bottom skin has a HDPE, core has HDPE, top skin has HDPE. Because HDPE is there in skin and core, they perfectly bond to each other. No doubt, there is again printing parameters you need to look into. I'll show some of the images. how bad samples also you can print. But this is what you need to do. But now, before going for experimentation, we did some FE simulation, very simple FE simulation, because we know that we had this printing temperatures, right? For HDP, what is the best printing temperature? For the composite, what is the best printing temperature? So we inputted these printing temperatures and we conducted steady state thermal analysis to just look around what are the stresses developed in the system. Okay. And then based on that, it is just rather to gain some good confidence that, okay, HDP can be printed. If I could say wide thermal stresses, then probably I need to look into the temperature parameters, and even we can change the temperature parameters in simulation and look around, so that will make the residual thermal stresses to be minimum most. So what you see in table 2 and table 3 and table 4. So table 2 is our, I think, 3 months work of optimizing the parameters. We did not use any optimization algorithm for that matter. All was 1:1 because here there is multiple, rather it would be a multivariate analysis. I actually wanted not to do that because I know the parameters, I know the material, I know the TG, melting point, degradation temperature. Let me first look at that at the experimental level, because please do remember, when I say chamber temperature of 90 degrees C, we set it at 90, but there are convection radiation losses, right? The same is with printing temperature, same is with the bed temperature. So all these things, so variations, mathematical model probably might not predict well. That's why we went with 1:1, and we rather done it on a pilot scale on an experimental level to just come up with the proper values. And we did that. So for N1 HDP filament, whatever you see in the square bracket, the bold ones are the optimized one. The range is 200 to 230. This is based on TG, melting, and degradation temperature. And this, we did do the experimental test. We did not believe on the supplier's data because batch to batch, there might be variations, grade to grade, there might be variations. So it is always better once you take procure the material, you do all the experimental, basic, fundamental physical investigations on that. So, and that's how we can narrow down to this 200 to 230. Similarly, for N2, that is H20, H is HDP, 20 is 20% volume fraction of glass microballoon in HDP. Likewise, 40 is 60. SH is sandwich. Okay, so sandwich with H20 as core, sandwich with H40 as core, sandwich with H60 as core. And here for sandwich skin, we kept it pure HDP, okay, because we want to resolve that first. And later you can, once you have all the mathematical models, experimental experience with you, then you can go with carbon fiber, carbon nanotubes, and then whatnot. You can go with natural fiber, artificial fiber, woven cloth for a skin, which will definitely give a better property. But at a pilot, at the first time, to crack the fundamental issues, we went with the pure HDP. And this is what all the parameters comes in picture. So we varied the temperatures. Then table 3, we used this material properties for FE simulation, and whatever material properties you see here, which you have fed it to FE simulation, are experimentally investigated properties values for a minimum sample size of 10. ASTM says, let us say if you go for H20, you test 5 samples and average you report. But for all the whatever we wanted to input in simulation, we went with one more factor of safety, went with 10 samples, and then the average CT values, thermal conductivity, specific heat, all these are, even density, all these are experimentally calculated with standard deviation less than 1.5%. So because in FE, if you input the properties correctly, then only it is going to give an closer estimation closer estimation to your experimental values. And then we had to do a lot of jugglery in deciding the substrate. Because as I said, I was talking about if you take an ABS, you put the ABS paste at the base so that it will have a first layer gets adhered to it and the subsequent layers will be printed without any hassles. So the same with HDP. When you want to have an HDP paste has to be prepared. But HDP dissolving is a great issue. No doubt there is a chemical, but there are many issues with it. So we tried a different substrates. So we tried with HDP tape, with bed heating, HDP tape without bed heating, with bed heating. Then there is a Kapton tape, heat resistant tape available in the market. But what came best is this Kraton ACBS FD1901. This polymer is readily available in the market. We had to modify that a little bit because in polymer chemistry we can go for some additives which will change the properties a little bit, but gives a better response for a specific application. We wanted to go for an adhesion. So as per that, we did some polymer additive addition and then come up with that, okay, this is the best, and that is what is being used for all the HDP printings. Does that print good? Definitely not. So these are all different failure slides and successful slides. So if you see this figure 4, these are all representative print images at 80 degrees C to 120 degrees C, 80, 100, 120, which is the bed temperature I am talking about, with 45 to 75 degrees C. So then we have chamber temperature range also, because all these parameters are very, very dynamic. Then for B, this one, we have sandwich 20. So you can see delamination here in the micrograph. With naked eye, you will say, oh, this is perfect sample. Okay, any sample if you choose. Then if you go for a micrograph, these are what layers we deposit one over the another. Okay, you can see a big, rather I would say crack because of non-proper diffusion of the core. This is core and this is skin, core and skin. But you need to optimize the parameters to get a perfect sample like which is seen in E. So these are the layers, and this is taken on the side, that is on this side. Okay, whatever you see here, this side. If you break it, then you will see all the filler contents there. So these are all those optimization juggleries which we did. Similarly, when you have printing temperature in N1 is for our HDP filament, N2 is for our foam filament. So we need to do that combination once you stabilize, once you choose a proper substrate material, once you choose a proper chamber temperature, then comes bed temperature, and then comes the printing temperature. So we went stepwise, so resolving issue one at a time. And then by having experimental different settings, we could able to come down with 225 for N1, that is pure HDP, and 245 for a particular our foam filaments. And you can see that there is no warpage, perfect smooth surface, then perfect bonding between the layers, and that is what you see in this micrograph as well. So there are many issues, like one more parameter is the prime filler, which you need to have it so that such defect, which is rather deposition with some variation, gets gets eliminated. Then comes the warpage, and you can see a warpage here. Now what happens? You print the sample. So here we say 120 degrees C is the best one. You print the sample. During printing, nothing happens. Absolutely nothing happens. Once the printing stops, the complete sandwich bends like this. Now you can see 30 millimeters from the table level. 30 millimeters is the warpage, and it is nothing but printing. I would say, in other words, printing of a curved panel. Okay, but this curved panel is not the intended one. We wanted a flat sandwich, and then by having 120 degrees C, we could able to print a perfect sandwich. So you can see the skin color different, core different, and the skin differently. So again, this is just a sandwich printing. If I go with functionally graded materials printing, which presently we are doing, already we have communicated around 3 to 4 papers there. Then functionally graded sandwiches, another 3-4 papers are under review. So I'll probably present that once the papers are out, or you can just locate them as and when you get. So just having a single core with the skin, these are all parameters which we need to really look into in details and optimize the parameters. Or I would say go for a suitable parameters. And by doing that, finally we landed up with a good sample. And there are something known as a layer offset. So this layer offset comes in because of a change in the nozzle distances. So you need to calibrate probably if your machine is running very often, then your calibration or measuring these offsets should be very often. In our lab, we do every week because our machine runs almost 24/7 for different material systems. Then some island formation, void pockets. These are all parameters which will come when you try different system. When you go for ABS, everything comes perfectly fine. Even you can make a ABS composite, then sandwich of that, because the material is known, and what numbers you saw in this table, in this table in table 2, is already available with the supplier of the material. And that's why we never face any difficulties when we go for conventional material systems or filaments which are available in the market. But when you do different compositions, definitely you need to you will face a challenge, and you can find a solution. That's not a much big deal. Now, I was talking about the micrograph on the edge, right? I'll just go back. Yes, here. Now here, yeah. So figure 7B, 120° C image. You can see a skin here. You can see a core and again a skin. So we took the micrograph on this edge, and then we broken the sandwich into 2 pieces, and then we took the micrograph across the edge. And that is what I'm showing it here. This figure 9C is a micrograph of sandwich along thickness. You can see a core and skin. The composition is different. Here we have microballoons. Here we don't have any microballoons. So once you choose a suitable parameter, this is what the perfect fusion happens. Now, when you break them, what you see is in A and B. Okay, so A is again the failed samples, wherein we were trying different combinations, and thereby you can see a skin here and core. Absolutely, there is no bonding at these pockets. Okay, these are known as residual microporosities. And sometimes people say that this is a non-raster. The single line is known as a raster for that matter when we print. So when they don't fuse well, so this is what the pockets you see. And these porosities are bound to happen. You can minimize them. Okay. So this is what A says, okay, for one of the samples, we, for one of the parameters, how the parameters were chosen differently, and thereby how the samples went bad. In B, you can see a skin, core, and skin. This is complete sandwich mapping. And you can see here seamless bonding between the skin and core. Core, no issue. Again, bottom core and the bottom skin. So this is the perfect bonding happened, and we can do that through some parameters. Then we did temperature distribution in sandwiches by putting the different values to just know how sharply the distribution changes. I'll not go in much details of this, but this anyone can do that. There's not a much big issue here. And this is what the temperature distribution or stress distribution in sandwich with 60 happened. This is the no load condition, only the temperature distribution I'm talking about. The top one will give you the maximum temperature because this is the last layer which got printed. Okay. And then we just plotted the temperature distribution across the thickness, the stress distribution across the thickness. Now these plots this simulation helps us in knowing what is that at interface, how does sharply it changes. Okay, so this is a core, this is the bottom skin have one stress, and then once it goes to the regime of core, suddenly the stress drops because we have a different material property, and that's what we wanted. And then slowly rises at the interface, again it shoots up and goes to the HDP regime. Now such a drop and rise tells us that this is what the residual stresses are there inside the sample. Okay, because we can't, there are methods, very expensive methods to experimentally measure the residual stresses. But in the absence of that, the simulation packages helps us in what is that range within which it is acting. And then we can do the annealing, we can do for again one more time, we can put it in the oven and just try to reduce this, and we can definitely do that. So prima facie with the existing suitable parameters, what are the stress levels? And because these values I should know, because if I want to use it in some mathematical models, I can take the help of them. And that's how the simulation packages supports the experimental investigations or further mathematical developments. So with this, I'll stop. So before closing the session, I would like to thank all my funding agencies, starting from DST, Office of Naval Research USA, National Science Foundation USA, DST SERB, ISRE. So with ISRE, I'm doing foam printing again for enhancing the thermal insulation. Then I have Spark One, wherein we are collaboratively doing work with University of Wisconsin for civil applications. And then VGST, which is the state government-led funding agency. So I thank all these people who funded my research and still funding them. So with this, I want to close and thank you for the patient hearing. It was a really great challenge because it is afternoon. So I hope I could able to reach you with whatever experiences I had. Thank you.
Participants can post their questions in the chat box. Participants, if you have any questions, sir, Maheshwaran is asking how to identify the stress distribution along the thickness of sandwich experimentally.
Okay. Experimentally, we can once you print a sample, you can drill a micro hole, and then there is one method experimentally, or we can go for X-ray diffractions. But during printing, really, it is not possible. There are now companies coming up with, or rather, you can do it. You need to put a thermal camera inside the chamber, which will focus or which will be connected to the nozzle. So as and when the nozzle is printing, it will go on capturing the temperature. It will build the heat map. But once the printing is done, what happens to each of these layers? So during printing, you can map it, but post printing, it is going to be a serious challenge. One way is this simulation packages. Second, experimentally, you can by destructively go for micro drilling and put the probes and sensors and measure it. That is possible. I hope I answered.
Thank you, sir. Any more questions?
And if there are any more questions, even if you have it at the later stage, you can always locate me at NITK website. My email ID is also there. You can post me a question, or if you need any more information, you can always ask.
Thank you, sir. So on behalf of the management and the Department of Mechanical Engineering, Dr. Mahalingam College of Engineering and Technology, we would render our fullest thanks to Dr. Mrityunjay sir for the wonderful session with us, for the 5 days FDP on 3D printing and design. Thank you very much, sir.
Thank you.
Thank you for your time and presentation.
Thank you. Okay, so wish you all the best. Good luck and be safe. Thank you.
Thank you, sir. This is Dr. Ramathirumurugan, professor from Mahalingam Engineering College, sir. Thank you very much for your wonderful presentation. Yeah.
Thank you.
Thank
you, sir.
Okay, so I'm dropping now.
The feedback form has been posted in the chat box. Participants are requested to fill the feedback form. We will resume our session by 2:30 sharp.